multi-step reactions. Okay. Uh, as this name suggests, right? So, multi-step reactions are the reactions which will occur by more than one steps. More than one step are involved in multi-step reactions, right? So, if you are to examine some examples, right? So, the carbocation mechanism, the carbocation reaction when it comes to alkyl halides, basically tertiary alkyl halides with the NUH, right? With nucleophiles, tertiary alkyl halides with nucleophiles, come across nucleophile substitution reaction, which will occur via two steps. More than one step is involved. More than one step are involved in this reaction, right? So like that. So those are the multi-step reactions, right? So sometimes by just looking at the reaction, I mean just looking at the chemical equation, we can say whether a reaction is elementary or multi-step. Not for all the reactions, but for some reactions, by just looking at the chemical reaction, the chemical equation, we can say it is a multi-step reaction or not, right? It's like this. But if you are to think of this kind of a reaction, they are 2A plus B and a C gives you some product, right? If you think of this kind of a reaction, you clearly see the summation of stoichiometric values of the reactants, the summation of stoichiometric coefficients of the reactants, right, exceed 3 units. The summation is 4, which is a greater value than 3. That means the molecularity seems like you are getting molecularity as 4 if this is elementary. That can't happen. Molecularity can't exceed the 3. No? So that this kind of a thing definitely should be a multi-step reaction, right? If the stoichiometric summation of the reactants exceed 3 units, definitely those reactions can't be elementary because molecularity can't exceed 3. Right? In elementary reactions, the molecularity is given by the summation of the stoichiometric values of the reactants. So if it exceeds 3, definitely those reactions should be multi-step, right? So for some reactions, by just looking at the chemical reaction, chemical equation, we can say whether it's a multi-step, right? So that is something you can clearly see by adding the calculated values, right, of the reactants, right? So that idea is represented at the first para, right, with the multi-step reactions, right? So let's go to that thing. For the multi-step reactions, it says, this page number 25, right? It says there are some chemical reactions whose molecularity appears to be more than 3 from stoichiometric equations. From stoichiometric equations, the summation of the stoichiometric values of the reactants sometimes exceed 3 units, right? So they have given some reactions there. 4 of HB are coming up with O2. So the summation of stoichiometric values of the reactants is 5 there. For the second reaction, the MnO4- reacting with oxalate and H pluses, right? If you are to come up with the summation of the stoichiometric values of the reactants, that will give you 23. So molecularity can't be 23. Molecularity can't be a value like 5. Can't exceed 3 units, right? So definitely these reactions should be multi-step, right? These can't be elementary, so that those should be multi-step because of only 2 types of reactions are available, right? If those are not elementary, definitely those should be multi-step reactions, right? So these should be multi-step reactions as the stoichiometric value of the summation exceeds 3 units, right? So the idea is clear, right? So they have given some right definition for the multi-step reaction. They are saying therefore a chemical reaction occurring in a sequence of 2 or more steps. in a sequence of 2 or more steps is called a multi-step or a complex reaction. Multi-step or a complex reaction, right? If the total process occurs by involving more than one step, right? 2 or 3 or more steps are involved to come up with the product, right? So then such processes are referred to as multi-step reactions or complex reactions, right? Okay, when it comes to multi-step reactions, there are 4 main things to consider, right? We have to consider 4 rules. Definitely, 4 rules are there with the multi-step reactions. So basic 4 points, right? So we'll come across one by one, and as those are given in the note, right? So the first thing, it says like this: chemical processes that occur in series of elementary steps have their own set of rules, right? One by one, let's discuss, right? So the first thing, the overall reaction is the summation of the elementary step. Overall reaction is the summation of elementary. We'll discuss these 4 things with some example. We'll discuss these 4 things, right? So it's like this, right? So I'll go with the example, right? So let's consider some kind of multi-step reaction. I'll explain you these 4 points with the example, right? So I'm going to discuss about this reaction, right? This reaction where your benzene, right? Benzene react with the, let's say, react with the Br2, right? In the presence of HPBr3 catalyst to give you the bromobenzene and some HBr, right? Let's discuss about this multi-step reaction, right? If you are examining the mechanism here, the steps involved at this reaction, right? The steps to involve here, right? So what are the steps involved in here? First, the reaction of these 2 guys. This is the first step. Br2 reacting with HPBr3 to come up with the, right, this one, right, Br, right, HPBr3. This is the first thing, first step. Then this activated nucleophile will attack to the benzene. This is your second step of this multi-step reaction, right? You know this thing happens right like this. Anyway, that step will give you this, right? Let's complete like this, and if we are 4 minus, right? Then we'll write some stabilization of the uranium ion, right? And ultimately we came up with this step, right? This is actually an example for kind of a multi-step reaction. Okay, yeah. So HCBr 4 minus, right? Ultimately reacting with those, right? Here this stuff will happen, right? So ultimately to give you this product, right? The HBr and the HPBr3. This is kind of a mechanism you know. It's kind of a reaction you know, which involves with 3 steps, right? Basically, here we have 3 steps, right? The other thing is not actually step, right? It is just showing the aromatic stabilization, the resonance stabilization of the uranium ion. That is actually not a step, but actually 3 steps are involved here, right? So let's examine the points, the rules of multi-step reaction, right? With the use of these things, right? So okay. First thing, the first rule. First rule of multi-step reaction. This is a multi-step reaction, right? Okay, this is your reaction. Above we have the reaction. These are the 3 steps. This is the first step, this is the second step, and this is the third step, right? The first rule, it says the overall reaction is the sum of the elementary steps. The overall reaction is the sum of the elementary steps. Yeah, the first thing to consider here is actually multi-step reactions are actually constructed with the use of elementary steps, right? You have 3 elementary steps here, you have three elementary reactions ultimately giving you the multi-step reaction, right? So first thing to consider is actually the multi-step reactions are actually a combination of elementary steps, right? In this multi-step reaction, reaction, three elementary steps are involved, right? A combination of elementary reactions or a combination of elementary steps will give you the multi-step reaction. That's the first thing. And you should note that the overall multi-step reaction is actually the summation of the elementary steps. The summation of all the elementary steps should give you the overall reaction, overall multi-step reaction. Let's see whether it happens here or not. If you add the three steps, if you add the step 1, 2, and 3, if you add the step 1, step 2, and step 3, don't you get this one? See, if you add the stuff right at the left hand side, right, only these two will remain. At the left hand side, only these two will remain. Why? Because this thing will cancel off with this one. Right, at the left hand side, you have one FBR3. And at the right also you have one FBR3. Those things will cancel off. And for this one, this thing will also cancel off as you have the same guy appearing at the right hand side as well. So these two will cancel off if you are to add these three together. Right? As well as this one. This thing will cancel off with this. If you add these three guys together, right, you are with FBR4 minus at the left hand side. So at the right, although you have the same stuff, right, so those will be cancelled off. So that if you add these three elementary steps at the left hand side, you will get only these two guys, which are not going to cancel off. When you add, you don't see any BR2, so benzene appearing at the right. Okay. So if you examine the right hand side, only these two will be there. Only these two will remain. Because this right hand guy will cancel off with this one. This thing will cancel off with this one. This thing will cancel off with this one. So that only these two will remain at the right hand side if you are to add these four guys. Right? So you can clearly see, right, the multi-step reaction is actually the summation of all the elementary steps involved. The summation of all the elementary steps involved will give you the ultimate multi-step reaction, right? That is the first rule, always applying in the multi-step reaction. See, it is said, right? The overall reaction is the summation of the elementary steps. It is understood. Do you have any question about that thing? In problem? This is right now. Okay. The summation of all the elementary steps will give you the ultimate multi-step reaction. That is the first row, right? The second, right? The second point, it says a species that is formed in one step and then used up in a latter step is an intermediate. So remember, there is always intermediates involving multi-step reactions. In multi-step reactions, there is always intermediate, right? Sometimes it may be a one intermediate, sometimes you may have more than one intermediate involved in multi-step reactions, right? So earlier, with the earlier discussion, when we are discussing about the elementary reactions, also we had discussed about this idea. So if you remember, right, the confirmation of an elementary reaction is actually done by, right, doing a practical and seeing that there is no appearance of an intermediate, right? That is the way of confirming whether a reaction is elementary or not. Right? If you are to confirm a reaction is elementary, you have to definitely check for intermediate, and you have to confirm that there is no intermediate there. Right? Then only you can confirm the reaction is elementary. That means if an intermediate is there, the reactions are not elementary, so that those are multi-step. So for multi-step reactions, like definitely there should be intermediates, right? Always intermediates are involved in multi-step reactions. It may be a one or two or more than two, right? So anyway, intermediates are involved. So let's try to identify the intermediates in this multi-step reaction. Yes, in this multistep reaction, let's try to identify the intermediate, right? So intermediates are the ones actually which will form in a step, and in a later step which will be totally consumed. So intermediates are the ones which forms first and consumes the entire thing at a later step. Right? Those are the intermediates. Here you clearly see this one, right? This one, this guy. This guy is kind of intermediate. This guy is kind of intermediate. So it is formed at a prior step and at a later step, right? It is totally consumed. This is kind of intermediate. This intermediate one, this intermediate one. Actually, this multi-step reaction involves two intermediates. We can clearly see another intermediate appearing here, right? So what is that second intermediate? Yes, that is this one, right? Right. We have another intermediate. So this is another intermediate which forms at a one step, and at a later stage it will totally consume. This is also an intermediate. This is the intermediate too. So you have two intermediates involved in this multi-step reaction, right? The intermediates are the ones which forms in a step and then totally consumes at a later stage, right? At a later step, right? And totally consume. Those are the intermediates. So clearly, you should be able to see the intermediates are not appearing at the overall reaction, as all the things produced in a prior step will be totally consumed at a later step, right? So that intermediates are not involving, or you can't see the intermediates appearing in the total reaction, right? So if you are to think of the multi-step reaction, so no intermediates are appearing there. So we have question there, right? Yes. So why? Yeah. So why is the FEBR4 not an intermediate? Oh yeah. Sorry for that. This is also intermediate. Yes, of course. It is also intermediate. Sorry. You have three intermediates here, no? Intermediate. Yes, of course. We are here with three intermediates. Right. Huh? Okay, we are with three intermediates in this case, right? So in multi-separation, yes, we can have more than one intermediate, right? So this is kind of example. Intermediates are the ones which will form first, and then the total will consume at a later stage, right? So that those won't appear at the oral reaction, right? So we have three intermediates, right? Okay. So those are intermediates, right? Those will be definitely there in a multi-step reaction, right? Okay. The third point, yes. The third point is going to be about the catalyst. Let's try to identify a catalyst here. So, yeah, the catalysts are the ones which will consume first. Which will consume first. You consume the CBR here. It is your catalyst, right? You consume the CBR here at a prior stage, and then ultimately it will be regenerated. It will be regenerated. Those are the catalysts. Those are the catalysts. Right? Catalysts are the ones which will consume first, and the same amount will regenerate again. So that the no net production, no consumption, no net consumption, no net production. If you have consumed X moles here at the beginning, you will produce the same X moles. Right? So no net consumption, no production. No net consumption, no production when it comes to catalyst. Right? You will consume the catalyst first, and then you will produce the same amount. Those are the catalysts. Again, I am telling you, the catalyst is not going to actually not you won't see the catalyst appearing at the reaction. Even though I mark the catalyst like this, catalyst is not going to be a reactant or a product. At the reactant side, you won't write the catalyst. At the product side, you are not going to write the catalyst. So catalyst is not going to be a reactant or a product. Normally we write it at the top of the reaction arrow. but it is not a reactant or a product. Means at the oral reaction, that is not appearing. Reaction, chemical reaction means a combination of reactants and the products. A combination of reactants and the products, right? That is what is meant by a chemical reaction. So the catalyst won't appear at the reactant side as well as the product side. So catalysts are not going to display in your chemical reaction. Those are not going to display in your chemical reaction, right? So the reason is clear, because the consumed amount will regenerate. The same amount will regenerate. So no net consumption, no net production. The reactants are the ones which will consume. The products are the ones which will produce. So, but when it comes to catalyst, right? So no net consumption, no net production. So those don't refer to as reactant or product, right? So catalysts, those are not going to write in chemical reaction normal, right? So those are catalysts. So you should be able to identify the catalyst and the intermediate. You should be able to differentiate the catalyst and the intermediate, right? So how to differentiate? The intermediates are the ones which you produce first and then totally consume. Intermediates produce first and then will totally consume. But when it comes to catalyst, those will consume first and regenerate the same amount, right? So in intermediates, they will produce, then the same amount will consume. That is about the intermediate. When it comes to catalyst, the consumption happens first, then the same amount will regenerate, right? So that is the difference, right? So you should be able to differentiate the catalyst and the intermediates appearing in your reaction mechanism, right? This is referred to as a mechanism, right? You know that, right? Okay. So see what it says at the book. This at the page number 26, the point 3, it says a species that is used in one step, a species that is used in one step and increases the rate of the reaction, then regenerate in a later step, is acting as a catalyst. Right? Normally those are not going to return in the chemical reaction, the overall reaction, right? Okay. Then fourth point, it says, right, neither intermediates nor catalysts are seen in the overall reaction rate law. So that is not mainly represented as a reactant or a product. So that you are not going to write it in the rate law as well. Because in rate law, right, we are coming up with only the reactant. Only the concentrations of the reactants are written with the rate law. At the rate law, you are only coming up with the concentration of the reactant. Rate is equal to K into the concentration of the reactant with their orders. But as catalysts and intermediates are not considered as reactants, those are not going to represent at the rate law. Those are not going to be seen at the rate law, right? Those won't appear at the rate law, right? So neither intermediates nor catalysts are seen in the overall reaction rate law. Got the idea? So that is all about the major rules applying in the multistep reaction, right? Okay. So some examples are given. See, this is a kind of good example between the catalyst and the intermediates, right? And get the idea that overall reaction is actually summation of these three elementary steps, right? Remember, the multistep reactions are always, right, produced by a summation of elementary steps. All of these are elementary steps, right? The summation of elementary steps will give you the multistep reaction, right? Okay, that is the first point, right? Okay, some examples are given. See whether you are able to identify the intermediate and catalyst of those examples. See, some examples are given here. Let's go to the example. Those examples are there, right? So, some examples are given. See, this is the these are two steps. IO minus AQ and H2O liquid. That is your first step. And is the second step, reacting with H2O2 liquid to come up with the I minus AQ and H2O liquid and O2 gas. Right? First thing, with the use of these two steps, we should be able to come up with the oral reaction, right? First thing is that with the use of these two steps, we should be able to come up with the oral reaction, right? Okay, they have mentioned this. Actually, these two steps are bimolecular, right? This elemental step is bimolecular. One, two. This elemental step is also bimolecular, right? So, two bimolecular steps, elementary steps, will give you the multi-step reaction here. To come with the multi-step reaction, what we do? Just addition of these two. Just the addition of these two guys will give you the multi-step reaction. Right? So that let's count with that. So if you add these two guys, right? These two we cancel out, right and left, right? And these two we cancel out. And what you will remain is 2 of H2O. 2 of H2O at the left hand side, and you get the 2 of H2O and 1 O2 at the right hand side. So that is the overall reaction. Right? That is the overall reaction. If you need to come up with the overall reaction when the mechanism is given, what you need to do is just add the elemental steps together. By adding all the elementary steps together, you get the overall reaction. Is the overall reaction, right? So then you should be able to identify the intermediate and the catalyst here. So what is the intermediate? Lamine. Put down here chat box. Chat box එක දාන්න මේක මොකක්ද මේක intermediate. What is the intermediate? Here, and what is the catalyst? Can you send me the answer? What is the intermediate here and what is the catalyst? So intermediate is the one which produce first. Intermediates are the ones which produce first, and then the total amount will consume. So what is the intermediate? Here the intermediate is IO minus. IO minus is the intermediate. This is the intermediate which produce first and then consume. So this thing is not appearing at the oral reaction, right? So IO minus is the intermediate. So you have some dotted lines there. IO minus is the intermediate. And what is the catalyst there? This is the intermediate. So intermediate is IO minus. Then what is the catalyst? So catalysts are the ones which consumes first and then it will be regenerated the same amount. So such a thing appears here. That is the imine. That is the imine which consumes first. It consumes first and then regenerates the same amount. One molecule consumes and one molecule produces as well. So the imine is your catalyst. So catalyst is I minus AQ. You clearly see these two guys are not appearing at the oral reaction. These two guys are not appearing at the oral reaction. For normal situations, for normal scenarios, the catalyst and the intermediates are not appearing at your chemical reaction. Right? For normal processes, the catalyst and the intermediates are not appearing in your chemical reaction. Right? Actually, if a statement is given like this, intermediates never appear. Intermediates never appear at the oral reaction. If such a statement was there, intermediates never appear in the oral reaction. Intermediates never appear in the oral reaction. If such a statement is there, that is true. Intermediates never appear at the oral reaction. Intermediates can be seen only in the nucleus. Intermediates never appear at the oral reaction. That is true. Intermediates never appear at the oral reaction. At the reactant side as well as the product side, you won't see intermediates appear. Right? That is about the intermediate. What about the catalyst? If a statement is there, catalysts never appear at the oral reaction. Catalysts never appear at the Oro reaction. What is your idea? Catalysts won't appear at the Oro reaction. That is true. If there is a statement like a catalyst won't appear at the Oro reaction, that is true. But if the statement is like that, catalyst never appear at the Oro reaction. If such a statement was there, what is your idea? What is your comment? Catalyst never appear at the Oro reaction. Is that true or false? Never. Always say never. If we have an exception, the statement is going to be false. If we can find out the exception, the statement is going to be false. Do we have an exception? Exception? Do you have such behavior cases with the catalyst? Yes, we do. We do have exception, which we know, which we definitely know. Haven't you heard about the self-catalyzed reactions? Self-catalyzed reactions. We have discussed that thing. Self-catalyzed reactions. When the reaction of oxalate happens with the KMnO4, when the oxalate ions are to oxidize with the KMnO4, the MnO4 minus will reduce to Mn2 plus. The so produced Mn2 plus will act as a self-catalyst. Right? That thing is there in the note, right? We had discussed about that in the catalyst, right? That was there in page number 40 and auto catalyst. At the bottom part of the page number 40, it is there. Auto catalyzed reaction. Self catalyst or auto catalyst, right? So Mn2 plus happens to act as a catalyst for the oxidation of oxalate with KMnO4. So the statement is not always true then. Normally catalysts won't appear. Normally catalysts won't appear at the Oro reaction. Normally catalysts won't appear at the Oro reaction. But that is not always. Right? Self-catalyzed situations are there. Oh yeah, and then if it is a statement like catalysts never appear at the Oro reaction, if such a statement was there, that is false. Because you add the product sides at that Mn oxalate thing, the Mn2 plus catalyst is at the product side, right? So that means it appears. They are the reaction. So any problem with that? Any questions regarding the thing we have just discussed? No. Sorry. එහෙනම් කතාවයි මම හරි. So උතර අපි නැතත් කියන මොකක්ද මේ කිව්වේ when it comes to intermediates they never appear at the Oro reaction. That is true. But when it comes to catalysts, normally they won't appear at the Oro reaction. Normally they won't appear at the Oro reaction, and sometimes it could be there, right? Okay, I have given you an example, right? Okay, that is about the catalyst. So another thing to discuss. So remember, if there is a catalyst involved, so we normally know if there is an intermediate involved, definitely it is going to be a multistep reaction. No? If there is an intermediate involved, definitely it's a multistep reaction. No? We had discussed that thing, no? Even at the last lesson. If there is an intermediate, definitely it's a multistep reaction. That is okay. If a statement is like this is there, if they have asked you a question like this, a statement indicating if a catalyst is involved, definitely the reaction should be an reaction should be a multi-step reaction. Again, I am telling in the statement. Comment whether it is true or false. The statement is if a catalyst is involved, the reaction should be a multi-step reaction. Reaction definitely going to be a multi-step reaction. What about that idea? Is it true or false? Comment. If a catalyst is involved, reaction should be a multi-step reaction. Is it true or false? If a catalyst is involved, the reaction should be a multi-step reaction. It is true. It is true. Definitely. Why not? It is true, right? Why? Because if a catalyst is involved, there should be a step to consume the catalyst and there should be another step to regenerate the catalyst. Definitely. There should be two steps. At least two steps should be there. At least two steps should be there to consume the catalyst and regenerate the same. At least two steps should be there. So it is becoming a multi-step reaction. That is logical, na? That thing is not written in your resource book. But such kind of question can be asked. Such a simple stuff. If a catalyst is involved, definitely there should be a step to consume that thing. And there should be another step to regenerate the consumed amount. Definitely, at least you should have two steps. If a catalyst is involved. So, if a catalyst is involved, definitely the reaction is going to be multi-step. It is a definite. Statement is true. Right? ඒ වගේ පොඩි question එකක් අහන්න පුළුවන්. හරි පොතේ ඉතින් කියන එක නෙමෙයි. හරියට පොතේ මේ resource book එකේ එහෙම දේවල් දෙන්නේ නැහැ. That is your knowledge, right? Just the knowledge. Just think of it. Right? That is the idea of a catalyst. That is the idea of a catalyst, right? You should consume at a first step, right? And you have to realize. Okay. So those are the few things you should know, and you should be able to guess, right? With the knowledge you gain here, you should be able to guess those things. That is the knowledge you should gain from these discussions, right? Okay. Alright. Here, right? Hi. That is all about the catalyst stuff, right? So let's examine the second example as well. So we have another example here. Okay. Before going for the second example, the rate law also written for this one. So how to write the rate law for this one? Write the rate law for this one. So rate is equal to K into the rate constant into concentration of reactant. The only reactant here is H2O2. We are just looking at the overall reaction, right? We are not considering the steps here, the overall reaction, right? Always rate law is written for the overall reaction. Right? So this into some order. This is the order with respect to the H2O2. This value is kind of an experimental value, kind of an empirical value. We should do some experiment and have to find out that value, right? Okay. So experimentally, we have to measure this value. So see, you won't see the appearance of intermediates of the catalyst. You won't see the appearance of intermediates of the catalyst at the rate law. At the rate law, we won't see the appearance of intermediates of the catalyst. See, got the idea? So that is all the idea we had to gain from the first 4 points, first 4 rules of catalyst, right? Okay, that is the first example. Let's go to the second example as well. It is there is a group as well, right? Okay. I'll take an example as well. This is the second example. This is the reaction of actually ozone converting to O2. Right? These are two steps of the reaction of converting O3 to O2 is given in your book, right? Then the ClO gas creates O3 gas to form the Cl gas and one CO4. First of all, this is the first step, and this is the second step. First of all, if you have asked to, if they have asked you to come up with the overall reaction, overall multistep reaction, what you have to do is actually just to adapt the two elementary steps and all the elementary steps involved in a multistep reaction, right? To come up with the overall reaction. What happens? If you consider the overall reaction, the right hand side, if you consider the right hand side, this Cl will disappear with this Cl. Those will cancel out. I'm just considering right hand side, right? This ClO, this right hand side ClO will disappear with this one. Cancel off with that ClO. So at the right hand side, only the two of O3 molecules will remain. So two of O3 molecules. That will be at the at the left hand side. When it comes to right hand side, right, three of O2 molecules will remain. So that is the overall reaction. As the intermediates and the catalysts are normally cancelled out, right? You will remain with the reactants and product, right? So this is the overall reaction. Let's try to come up with the intermediates and the catalysts here. The intermediates. What are the intermediates? First they should consume. Sorry, first they should produce and then only they will consume. Produce first and then consume. So such a guy. That is this. ClO gas first produced, then it consumed. So that is the intermediate, right? Your intermediate. Your intermediate is ClO gas. That is your intermediate. What about the catalysts? The catalysts here. The catalysts are the ones which consumes and then regenerate. Which consumes first and then regenerate the same amount. That is this. First consumes and then regenerate the same amount, the same one molecule. So that is the catalyst. So your catalyst is Cl gas. That is clear. And when it comes to this thing, if you have asked, if they have asked you to come up with the rate law can be written like this: K into the reactant, the concentration of reactant or gas into some X, which should be experimentally determined. This X is kind of an empirical value, which should be experimentally determined, right now. So that is the rate law. Again, we see with the rate law, we are not going to write the intermediates or the catalyst. Only the reactants are involved at the rate law, as intermediates and catalysts won't appear at the reactant side of a reaction. So those are not going to be written here at the rate law. Right? Got the idea? Right? That is all about the second example, and you can go to the note there in the book. The things are appearing. Right? See? Alright. If you have any questions, you can ask now. Questions again. No question. ප්‍රශ්නයක් right? මොකද අර අපි මේ පොඩි examples දෙකක් එක්ක right අපි පොඩි idea එකක් ගත්තේ multi-step reactions කියන්නේ කොයි වගේ දේවල්ද කියන එක. Right. Next one. Let's continue. This is the bottom part of page number 26, right? Then we'll discuss about the rate determined step here. So as number of steps are involved with multi-step reaction, as more than one step, right, involved in this multi-step reaction, right, there should be a specific step as the rate determined step, right, as more than one step are involved, right, there should be a specific step which will determine the rate of the overall process, right. So you already got the idea about that Macabas and stuff. Matagani or Macabas when he used to build up the Cleopatra castle, right? Cleopatra castle level the Macabas Matagani, that's how it's remembered. No? So there we had mentioned that the slowest step, the slowest process will determine the rate of the whole process. The slowest step will determine the rate of the whole reaction, right? Whole process. That was the idea with that story. Okay, right? Now, when it comes to multi-step reaction, they are also the slowest step. The slowest step will determine the rate of the overall process, overall multi-step reaction. The rate of the overall multi-step reaction will be determined by the slowest step. So that in a multi-step reaction, the slowest step is considered as the rate determined step, right? So in a multi-step reaction, the slowest step is considered as the rate determined step because it will decide the rate of the overall process, the whole process, right? In a multi-step reaction, rate determined step එක එයාගේ source step එක, right? එයාගේ source step එක, right? But right. Okay, so that is the normally the normally actually the rate determined step of a multi-step reaction is the source step, right? Of all the those step of the overall process, right? Okay, see, it is said here. If the bottom part of the page 20 is right, it says rate determined step of a multi-step reaction and molecular rating. That was the topic there, and it says at the first point, when considering the mechanism of a multi-step reaction, there are steps which will occur slowly, and there are steps which will occur at a higher speed. Here, the rate of the overall reaction is determined by the source step, and so the source step in the reaction mechanism is considered as the rate determined step. So rate determined step of a multi-step reaction is actually the source step of the reaction mechanism, right? Okay, it is considered the RDS. Simply, we know it as the RDS, rate determined step, right? Next point, it says in an energy profile of a multi-step reaction, the RDS is the step with the highest activation in RDS is the step with the highest activation in, right? RDS is the step with the highest activation energy, right? So let's consider what was that? බලමු මොකක්ද ඒගොල්ලෝ ඒ කතා කරේ කියලා, right? මොකක්ද ඒ දැන් ළමයි හරි දැන් අපි පොඩ්ඩක් මෙහෙම ඉදමු. Let's consider this, right? Let's think of this, right? මෙහෙම ඉදමු. අපි නිගමන ඉදමු. අපි නිගමන ඉදමු. හරි? මේ ස්ටෙප් එක, right? මේ ස්ටෙප් එක තමයි ඔයාගේ ස්ලෝ ස්ටෙප් එක කියන්නේ. නිගමනනේ අපි assign කරමු. This is your fast step. නිගමනනේ assign කරමු. This is your slow step. Slow step and this guy is kind of fast step, right? So this is the multi-step reaction, right? This is a multi-step reaction, right? Involving two steps. Let's try to come up with the energy profile of this stuff. What are energy profile level? Tell me, energy profile right here. Now we are to draw the energy profile of this multi-step reaction. Energy profile of multi-step reaction. The overall reaction is this. Overall reaction is 2O4 gases converted into 3O4 gases, right? Okay, let's write the energy profile. by considering this is slower step and this is a kind of a fast. We just assign, right? I just assign them that, right? As this term is as the slower step, right? So it's like this. So in an energy profile, if you are to consider this guy is kind of exothermic, if you are to consider this guy is kind of an exothermic, the energy profile would look like this. It's an exothermic reaction. So that the starting point, which is with the O3 gas, 2O4 gas, and the end point, right, which is with 3O42 gas, this is the overall reaction, right? That should have a exothermic enthalpy change. Delta T is minus, right? This is how we draw exothermic energy profile. In enthalpy, we have studied them, right? In exothermic reactions, the energy has released to outside so that this energy of system will decrease eventually when the reaction happens. That is what we meant by exothermic. At the start, you have more energy. As the reaction is exothermic, you have released some energy so that you will come up with, ended up with a lower energy state, right? That is how that is what we mean by exothermic, right? If an exothermic reaction is there, definitely the product state should be lower than the reactant state, right? In your energy profile, right? In your energy profile, in your energy, right? This is your reaction coordinate, right? So this is not the case what we are going to refer here. We are going to discuss about the lower step and the activation of the stuff. Now we are going to consider the slower step and what is the importance of the activation of that step for a reaction, right? They like this. So the thing is, when we are considering these two steps, right? This one came as a slower step because this one is considered as a slow step because less number of products, less number of products, less number of products will form in a unit time for this step than this. That is why we consider this one as the slow step. Like that, no? If one to consider a step as a slower step, at that step, the number of products produced should be lower than the other step. And if you are to consider this, let's consider this step happened 5 times per second. This thing happened 10 times per second. That means this is slow. That is the idea. So, what is the reason for that? One reason for giving you less number of products. One reason for giving you less number of products at this step is actually the higher activation energy barrier. If you have a great activation energy barrier, reactant molecules which are capable of overcoming that activation energy barrier is less. So that to the product village, only few molecules will come. Only few molecules will come. Only few reactant molecules will come to the product village if you are with a greater activation energy barrier, greater hill to climb, right? So that one reason to give you some less amount of products here is actually the activation energy barrier. If you are with a great activation energy barrier, less molecules will overcome that thing and come to the product village. That means your reaction rate will be low. So remember, in an energy profile, the slowest step is the one with the greatest activation energy barrier. Slowest step is the one with the greatest activation energy barrier. Because it is the greatest activation energy barrier, that is why only less amount of molecules will convert to products there. That is why it is giving you a slower rate, right? So remember, for your slower step in your energy profile, you have to come up with the greatest activation energy barrier. So you are with two steps like this. This is kind of one step. This kind of second step. Anyway, the activation energy barrier here. The activation energy barrier here. If it is so denoted as E1, EA1, activation energy barrier for the first step should be greater than the activation energy barrier here. If you are to consider it as EA2 for the second step, right? That is the idea. That is the whole idea. If your first step is the first step, the activation energy barrier means the difference between the energies of the reactors of the first of that step and the height. The difference between the energies of the reactors of that step and the height, right? That is the activation energy barrier. That should be greater than the activation energy barriers of the past steps, right? With the slower step, you should have the greater activation energy barrier. So this barrier is greater than the activation barriers of other steps. That is why this is considered as the third step, the first step one, right? This is kind of a two-step profile, energy profile. This is the first step. This is the first step coming from here to here, here to here. That is the first step. Here you have intermediate. This is the second step coming from here to here. This is the second step coming from here to here, here to here. Right? That is the second step. This is the first step. Here to here, first step. Here to here. This is the first step. This is the second step. This is the reactants of the second step, and these are the products of the second step. These are the reactants of first step, and these are the products of the second step. First step, right? So this is your first step, and this is your second step. This is the activation energy barrier of the first step. This is the activation energy barrier of the second step, right? But you should note that is actually with the slow step, you should have the greatest activation energy value. This value is greater than this smaller value, this is greater value. Right? So that is the idea, which is mentioned at the final statement of the page 20. It says, in an energy profile of a multi-step reaction, RDS, the first step, is the step with the highest activation value. Right now? Got the idea? Alright, so මේක තමයි පළවෙනි කාරණේ ඔළුව විදියට දාගන්න. මොකද්ද? In a multi-step reaction, the slow step is considered as the rate determined step, RDS, and it is with the greatest activation energy value. The slow step is with the greatest activation energy value. That is why it determines the rate. That is why it gives some less amount of productivity time and determines the rate. Becomes the slow step and determines the rate. Right now? Okay, so that is how the things are to be pictured, right? In a multi-step reaction and an energy profile of that, right? If you consider energy profile, this kind of energy profile, the first step is considered as the source step or the rate determinant step, and the total thing is kind of a exothermic process. The reaction is kind of exothermic process according to this profile, right? Alright. Are you okay with drawing this pathway? Lamai, when it comes to energy profile, right? These three things are actually the same as the enthalpy diagram. These three stages are actually the same like the energy profile you draw in enthalpy lesson. Enthalpy lesson එකේ ඔය අඳුනේ energy profile එක තමයි මේ ටික. මේ තුන ළමයි ඔයා enthalpy lesson එකේ energy profile එක තමයි. හරිද? මේ energy profile අලුතෙන් තියෙන්නේ මොකද්ද මෙන්න මේක. The reaction pathway. The reaction pathway is the new thing to learn here at the kinetics. But the other things are same as the energy profiles you have drawn in the energy lesson, enthalpy lesson. The only thing here to learn is actually how to draw this reaction pathway, this curve. But the stages and the other things are same as the energetics. Right there? Alright. So that is how the things are written. I mean, I'll discuss how write these stuff correctly. This is not the correct diagram. This is just a simple idea. Here the intermediates appear and here the reactants appear and here the products appear. It's kind of a simple idea, but this is not the complete diagram, right? We discussed about the complete diagram at the next question. At the next example, we'll discuss the complete diagram. But here, what I need you to give is actually the source step or the rate determined step should have the greater saturation energy barrier, right? That height, that heat should be with a greater height than the other step, right? The source step should have the greater saturation barrier. That is what I need to mention here clearly, right? With this diagram. The drawing, the other things will be discussed with the next example, right? Okay, let's go to the note there. You can clearly see this stuff, right? Okay, you can clearly see this stuff, right? This kind of diagram is appearing, right? They are at the note. At the page 27, you can clearly see kind of a diagram is appearing. Right, that source step is with the greater saturation energy, right? At the left hand diagram, it is considered the first step as a source step. As the left hand diagram, the diagram is this, after this diagram is there, and considered the first step as the source step. But at the right hand diagram, at the right hand side diagram, it is drawn considering the second step as the source step. At the right hand side also you have a diagram. They have considered the second step as the source step. At the right hand side diagram, they have considered the second step as the source step. If the second step is going to be the source step, right? And they went with the endothermic thing. That is also to be mentioned, right? This kind of endothermic situation, you clearly see kind of rise in energy when going from reactant to products. So you have the reactants here. You have the products here. Right? If you consider this energy profile, going from reactant to products, the energy has increased. That means you have to absorb some energy. So do the change now in your note, right? At the tagline with the second diagram, it is mentioned as an exothermic reaction, but mention that as a endothermic. It should be endo. Correct that. This is a kind of endo. At the second diagram, it should be a endothermic, right? Correct that thing. It should be endothermic, right? So reaction coordinate is there. You have energy here. Right? They have considered the second step as a determined step. So second step is your determined step, right? So if the second step is your determined step, that should have the greater activation than the others. So EA2 is greater than the EA1. If the second step is already determined, this is slow step. See? Right? According to this diagram, if you consider second step as a slow step, if the second step is your slow step, this is half. If second step is your slow step, then the diagram would look like this. Right? So this side, this is the second step. This is the first step. Coming from here to here, coming from here to here to produce the intermediate. That's the first step. This is the first step. This is the second step. Here to here, second step. This is the activation energy value of the first step. This is the activation energy value of the second step. Now, activation energy barrier is the energy difference between the reactants and the height of the corresponding step. Reactants and the height of the corresponding step. The energy difference is the activation energy value. For the second step, this is the reactant. This is the height. So the activation energy value is this. The difference between the reactants and the height. This much. Right? That is the activation energy value. Activation value is the difference between the reactants and the height of the peak for the corresponding step. This is the second step. These are the reactions of your second step. This is the height. That is the value. So as you consider this second step as the first step, you should have the greater saturation energy barrier among the steps, right? So those are two possible diagrams, right? For multi-step reaction. Okay, so मैं पहले नहीं do you have any question about these energy profiles? In this case, we have considered the first step as the third step, predetermined, as it is the greater height acquisition value than the other step. In this case, we have considered the second step as the source of the predetermined step. That is why we put some greater height there as the acquisition value than the other steps. Right now? Okay. How much is the activity? What is there? මේක ගොඩක් නේද? හරි. දැන් අපි ඉගෙන ගත්ත තමයි මල්ටි ස්ටෙප් රියැක්ෂන් එක rate determined step එකේ activation energy කියන්නේ. Now we have discussed about the activation energy of the rate determined step, the source step of a multi step reaction. That was our discussion up to now. We were discussing about the activation energy of the slow step of a multi-step reaction, right? Activation energy of the slow step or the rate determined step of a multi-step reaction. That's what we discussed. That should be with the greatest height, right? It should be a greater value than the other step, right? Okay, that is understood, right? I am going to come up with a new idea, another idea, new one. The early discussion was about the activation energy of the slow step. Now, what is your idea about the activation energy of the overall process? What is your idea about the activation energy of the overall process? Activation energy of the whole multi-step reaction. What is your idea about that? Activation energy of the whole process, whole multi-step reaction. Let's consider this diagram. Tell me the activation energy of the whole process. Is that the E1, EA1 or the EA2 or any different value? Tell me. Activation energy of this whole process. This is not about the first step. I am just saying the activation energy of the overall process of this diagram. Is it the E1, EA1 or EA2 or any other value? For this diagram. Not for the other, for this diagram. Left hand side diagram. Yes, any other answers? On these given some answers. What about the others? Activation energy of the overall process. What is the idea of the activation energy? You should know that. The minimum energy a reactant molecule should have to overcome the energy barrier. The minimum energy a reactant molecule should have to overcome the energy barrier to come to the product state is referred to as the activation energy. Again, try. What is the activation energy of this overall process? Overall multi-step reaction. Is it the EA1 or EA2 or any other value? Yes. Now, කැමති ඔයගොල්ලෝ answer දැනගන්න. I have given you the definition as well for the activation. Just try. In this case, yes, you are right. Right. In this case, the value is actually EA1. Value is actually EA1. Why I am saying so? Just think of that. What about this? What about this? With this energy profile, what is the idea? For this energy profile, what is the overall activation energy of the reaction? What is the activation energy of the overall process? Overall multi-step reaction. What is the activation energy? Is it the EA1? Is it the EA2? Or any different value? EA1, EA2, or any different value? Just come up with the definition. Just think of the definition of the activation energy. That is the minimum energy a reactant molecule should have to overcome the energy barrier. The minimum energy reactant molecule should have to overcome the energy barrier. That is the activation energy. For this process, the activation energy is not the E1, it is not the EA2, it is a different value. It's a different value. Right? The activation energy for this overall process is kind of a different value. Even though the slow step is with EA2, the slow step is with the EA2, the activation energy of the overall process is actually a different value than the EA1 or EA2. What is the idea there? What is the idea there? Very simple. I have already mentioned activation energy, right? Again, I am telling you, activation energy is the minimum energy needed to overcome the activation, overcome the energy barrier to come up to the product state. To come to the product state, the minimum energy needed to overcome for reactant molecules. That is the activation energy, right? Here, you have the reactant molecules here. These are the reactants. So the maximum height in this route, the maximum height in this route is this. The maximum height in this route is this. So the activation energy barrier is this. That is same as the EA1. That is same as the EA1. The maximum height, the maximum peak of this route is this. So your reactor molecules are here. So minimum energy needed for these guys, to overcome the maximum height of the pathway is this much. That is equal to EA1. That is why I say with this mechanism, this energy profile, the activation energy of the overall process is this. It is equal to EA1. Right? What about this? The maximum peak, the maximum height of the pathway is here, here. So your reactor molecules are here. So the minimum energy these molecules should have to overcome this barrier to come to the product state is this much. This is your activation energy of the overall process. Minimum energy needed for these molecules to overcome the energy barrier is this much. This route is with this kind of energy barrier. So here the activation energy of the overall process is greater than the activation energy of the source state. The activation energy of the overall process is this much. It is greater than the activation energy of the source state. That is what happens. That is what happens when the slow step is not the first step of your reaction pathway. If the slow step is not the first step, this is what happens. The activation energy of the overall process will be a greater value than the activation energy of the first step. But if the third step is your first step, if the third step is your first step, activation energy of the overall process may equal to the activation energy of the third step. May, right? Not definitely. It may or may not equal. It may equal. Right? Got the idea? Any questions? Actually, just write the things you need. Correct. Now, about the earlier Katagram, major professors again. The other discussion energy professors again. This session is very important one. This is about all about energy profile, right? Very important stuff, right? Okay. Let's discuss a bit more about the things we have discussed. දැන් අර මම කිව්වා හරිද? මොකක්ද කිව්වා? ඔයාගේ first step එක second step එක first step එක නෙමෙයි නා. ඔයාගේ first step එක නෙමෙයි නා. Definitely the activation energy will be greater than the activation energy of the third step. Definitely. This definite. හරිද? දැන් ඕගොල්ලෝ අහන ප්‍රශ්න මේ අහන්නේ මම. දැන් ඕගොල්ලෝ අහන ප්‍රශ්න මේ අහන්නේ. දැන් ඕගොල්ලෝ ප්‍රශ්න වලින් අහන්න තිබ්බා. ඒ එහෙම වෙන්නේ නැහැ නේද කියලා. දැන් අහන්නේ නැහැ නේද? මම කියන්නේ ප්‍රශ්නේ හරි. දැන් මේකේ ප්‍රශ්නේ. දැන් කාටද ළමයට මෙහෙම තර කරන් තිබ්බා. මෙන්න මේ ප්‍රශ්නේ අහන්න තිබ්බා ඕගොල්ලෝ. මම මේ ප්‍රශ්නේ කියන්නේ. මොකද්ද මම කිව්වේ? If the first step is not your first step is not your predetermined step, then your activation energy of the overall process will be greater than that of the third step. That is definite. That is what I have said, right? So one may ask this kind of question. සාමාන්‍යයෙන් ඔබ පන්තිදී කරද්දී ළමයි මෙහෙම ප්‍රශ්න අහනවා. ඇඳලා අහන්නේ ඉතින්. දැන් මේ මේක ඇහින්නේ නැතුව සමහර ඔයගොල්ලෝ මේ පොලයක් එන්න දීලා වෙන්නේ නේද? බට් මේ ප්‍රශ්නේ අහන් තිබ්බා. right? මොකක්ද මේ ප්‍රශ්නේ? මෙන්න මේක. හරි. දැන් ළමයට මෙහෙම එකක් අහින් තිබ්බා. If someone draw like this, this is a very important point. Right? If someone draw like this, හරි කාටද මෙන්න මෙහෙම එකක් ඇඳුවා. මෙහෙම දිනනවා හරි. energy reaction coordinate. or මෙහෙම අදිනවා. මෙයා second මෙහෙම. දුක් කතාවක් කියන්නේ වැදගත් කතාවක් කියන්නේ. This is EA1. The activation of the source step is this. Activation of the overall process is this. Then behavior of the activation of the overall process is less than that of the activation of the source step here. Here also, first step is not the source step. What is the problem with this diagram? We have issue with this diagram. What is the problem? මොකක්ද මේ diagram එකේ අවුල? These are reactants. This is the product state. This is the intermediate state. Do you see any issue with this diagram? මේ diagram එකේ ප්‍රශ්නේ මොකක්ද? මේ diagram වැරදි. මේ diagram අදින්න බෑ. සාමාන්‍ය ළමයි වගේ ඔය ගණන් ගහන ප්‍රශ්නේ අර මෙහිම diagram එකක් තිබ්බොත් මේකේ සර් කියපු කතාව වෙන්නේ නැහැ නේද කියලා. මොකද්ද මම කියපු කතාව? මම කිව්වේ ඔයාගේ first step එක නෙමෙයි නම් slow step එක. මම කිව්වේ overall reaction activation energy එක. හැම එකම higher value එකක් කියලා. slow step එක activation energy value එකට වඩා. That was what I said. Sometimes students draw this kind of diagram and ask, what happens if the diagram is like this? This is not fulfilling what you have said no. Such kind of questions are by some questions, right, when we are discussing this service, right? So what is the problem with this? Problem में मेगा प्रश्न हर मेरे दिन आउट मेगा the problem with the issue with this diagram is actually here. This is the problem. This is the problem. This is the problem. Always keep in mind. Always keep in mind. Intermediates are not stable compared to reactants and products. Intermediates are less stable compared to reactants and products. The lifetime of intermediates are very small. The lifetime of intermediates are very negligible. They just produce and just disappear. Just produces and just disappear. Lifetime is very small. That is why we won't see the intermediates appearing after the reaction. That is why we won't see the intermediates appearing before the reaction. And the reactor side, you don't see the intermediates. You don't see the intermediates at the product side. Because their lifetime is very small. They just produce and just disappear. Very negligible lifetimes with intermediates. That means those are not stable. Those are unstable. Those are unstable than the reactants and the products. So that the energies of intermediates should be greater than the reactants and products. It can't be like this. In this diagram, the energy of the intermediate state is less than the reactants and the products. That can't be. This kind of diagram says that intermediates are stable than the reactants and products. That can't be. Lesser the energy, stable you are. This diagram says the intermediates are stable than the reactants and products. That can't be. That is the problem with this diagram. You can't draw this kind of diagram. Always the intermediate state should have a great energy value than the reactants and products. You see, this intermediate state is the great energy value than the reactants and the products. You have the reactants here, the intermediates are with the great energy value. You have the products here, intermediates are with the great energy value than that. So it is unstable with great energy than the reactants and products. Intermediate state. Here as well, you see, these are correct diagrams. Intermediates are with great energies than the reactants as well as the products. So these intermediate states consider less great energy, those are unstable than the reactants and products. So you can't draw this kind of diagram. This diagram is false. This diagram is false. As you have to write the intermediates with some energies greater than the reactants and products, definitely if your first step is not this slow step, the overall reactions activation energy will be a greater value than the activation energy of the slow step. So that is always valid. That is always valid. As intermediates are with greater energies than the reactants and both the reactants and the product. I wish you got the idea. Correct. Right? I can't write all the stuff right there. Just write the things I have and discussing, right? When you are going through the video again also, you can copy these things in your notes, right? ඉතින් MCQ questions අහන්නේ කොහොමද? ඔකේ දින එකේ එහෙම statement එක ආයෙත් අහන්නේ නැහැ. හරි? ඔය ඉතින් අහන්නේ. පොඩ්ඩක් මේ කීනේ වැදගත් වෙයි ඔයාලට. හරි ඔය පොත ඔය නෝට්බුක් එකේ තියෙන්නේ ඔයගලගේ මේ ටියුටර් දීලා තියෙන්නේ අපි මේ රිසෝස් බුක් එකේ තියෙන දේවල්. ෆික්ෂන් සහක් ධ්‍යාන එහෙම නෙමෙයි. හරි ඒකට රෙඩි වෙන්න. හරිද? කතා බහලින් මේ දේවල් මුලට ගන්න. Always the intermediate state should be with a greater energy value than the reactants and the products of the overall reaction. Than the reactants and products of the overall reaction. Good idea. Right. That is all about the intermediate state. Pahali, hur? Thing in diagram they there no is our engine profiles bigger there no is. Just go to the two engine profiles. Just go to the engine profile. Correct. Engine there. Because my engine profile कोड़ा उड़ीन दिए लेगा कोड़ा कॉपी करता करूँ. There is some note regarding the molecularity of multistep reactions. We have discussed the molecularity of the concept of molecularity last week. Last week we had discussed the concept of molecularity, right? That is the minimum number of molecules which collide. Minimum number of reactant molecules. Correct. Yeah, that is the minimum number of reactant molecules which collide in the rate determined state. That was the idea of the molecularity. Minimum number of reactant molecules which collide to give product in the rate determined state. That is what is meant by the molecularity. In elementary reaction, as you have only one single step, the stoichiometric value becomes the molecularity. But when it comes to multi-step reactions, right, the idea applies. First you have to come up with the slow step. First you have to come up with the slow step, the rate determined step. First you have to come up with the rate determined step. Then you have to look the number of reactant molecules. Then you have to look the molecules at the reactant side of the rate determined step. And then you have to count 1, 2 like that. Then that number is your molecularity. So the molecularity of multistep reaction is actually the number of reactant molecules appearing at the slow step of your mechanism. That is the molecularity of the multistep reaction. That is the idea. Let's go to that point there. It says the minimum number of reactant particles that comes together or collide in a rate determined state or the slow state to form a product or products is called the molecularity of multistep reaction. I think you got the idea. Alright. So multistep reaction and molecularity first you have to choose the slow state of the reaction mechanism. That is your rate determined state. Then count the number of molecules at the reactant side of that state, slow state. That is your molecularity of a multistep reaction. Okay. That can't exceed 3. That can't exceed 3. Because multistep reactions are concerned with elementary step, right? So in an elementary step, the slow step is also an elementary step. Slow step is also an elementary step, right? Also an elementary step. So that the molecularity can't exceed 3 for that step as well, right? So always the molecularity will be less than 3, even for multistep reactions, right? Alright, you got the idea? Right, that is done. Clear up now? Any questions up now? Then we are going for another good example. So before going to that example, do you have any issues there to discuss? Any problems? Now අපි 2 minutes වගේ break 2-3 minutes break එකක් ගමුද? හරි අපි ඊට පස්සේ යනවා ළමයි ලොකු වැඩක් කතා කරන්න. හරි ලොකු වැඩක් කරන්න යන්නේ. ලොකු වැඩ කරන්න කලින් අපි 3-4 minutes break එකක් ගමු. මේ right now 4-5 minutes විතර class එක ගියයි. හරි පොඩ්ඩක් එකට set වෙන්න අපේ පොඩි break එකක් කරන් ඕන්න වතුර එකක් බීලා මේකට ලගින් දෙන්න. right So we'll discuss the lesson day. ඉස්සරහට අපි යන්නේ පොඩි ලොකු වැඩක් තියෙනවා. So we'll have a break for 5 minutes, right? Right. Here we are going to discuss about few things. Right. Here we are going to discuss about basically two things. Right. Main two things. Right. This discussion. Right. The two things are the one thing. The first thing. First thing we are going to discuss here is to derive the rate expression. To derive the rate expression when the mechanism is given. That is the first thing we are going to discuss here. This next session. But I am going to discuss with you how to derive the rate expression, but when the reaction mechanism is given. Up to now, we have discussed two ways of deriving the rate expression. Right? Actually, one is when the data are given in the form of a table. When the data are given in the form of a table, we had learned how to derive the rate expression. That was the last day's lesson. Right? Then before that, we have discussed how to derive the rate law when the data are given in the form of a table, in the form of a graph. The data are given in a form of a graph. If the graphical data are given, we had discussed how to derive the rate law. Those two ways have been discussed. Today we are going to discuss about the third method. The third question type they will going to ask you. Right? They will give you the reaction mechanism, and they will ask you to derive the rate law with the use of that mechanism. Right? That is the first thing we are going to discuss here in this discussion. Then after that we'll discuss how to construct the energy profile. That was the second discussion to go with. After the rate law thing, we'll discuss how to draw an energy profile, how to construct an energy profile. That will be the second discussion we are going to discuss now. Right? Hi. Now, මුලින්ම අපි discuss කරමු how to come up with the rate law when the mechanism is given. Right? We'll discuss that. Okay? Right? 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 Okay. Let's start that. Okay. We have some examples. Right? We'll go to those examples. Right? The first example is this. Right? They have given us this oral reaction, this oral multistep reaction. Right? This oral multistep reaction is given, and they have mentioned that this oral reaction happens in two steps. Step 1 is given as this NO2 gas with H2 gas with some K1 rate constant, giving you this, and the step 2 is this. where the NO2 meets some fluorine with the K2 and the NO2 is. They have mentioned that this is slow and this is fast, right? So our first discussion is how to come up with the rate law, with the use of this mechanism. That is what we are going to study first, right? This is example one. Right? We will study how to come up with the rate law with the use of this mechanism, right? It is like this, very easy, right? Very easy. One can write like this, no? You can write the rate of the overall process. You can write the rate of the overall process as the rate of the slower step. The rate of the slower step. Are you agreeing with me? Are you agreeing with me? මාත් එක්ක ඉන්නවද ඔයගොල්ලෝ? Rate of the overall process is actually the rate of the slower step. Anyone having a doubt about that thing? No? Shaming? Rate of the overall process is the rate of the slower step. That is understood. Right? Rate of the slower step or the rate driven step. Right? This is the slower step. Then we can write the rate of the slower step as it is elementary. As it is elementary. The multi-step reactions are constructed with a combination of elementary steps. Multi-step reaction එක හැදිලා තියෙන්නේ elementary steps combined වෙලා එකතු වෙලා. So slow step is also an elementary step. All the steps involving in multi-step reaction are elementary. So slow step is also kind of elementary. So we can write the rate of the slow step as the rate constant of the slow step, which is K1, into concentrations of the reactants of the slow step. The rate of the slow step is the rate constant of the slow step into concentration of the reactants of the slow step into their order. And what we know is when we are considering elementary things, the orders becoming the stoichiometric values. So we can write the rate of the slow step as K1 into NO2. If stoichiometric value is 1, we can put the stoichiometric values as their orders and F2 to the power 1. Why we are able to write like this? Because the slow step is also an elementary step. All the steps involving in a multi-step reaction are elementary. So as the slow step is also a kind of elementary step, you can write the rate of the slow step by assigning the rate constant of the slow step and the concentration of the reactants of the slow step with their stoichiometric values. Because the orders becoming stoichiometric values when we are considering elementary steps. So the rate is this. So no need to put the 1 here. Power 1 is understood. No need to put the 1 there. So you can write the rate like this. Right? After coming to this step, you have to look whether any intermediates or catalysts are appearing here. Or you have to check whether only the reactants of the overall reaction appears here. Because remember, for the rate of the overall reaction, we can only write the concentrations of the reactants of the overall reaction. Right? To consider the rate law of the, if you are writing the rate law of the Oro reaction, the rate law of the Oro reaction should contain only the reactants of the Oro reaction. So you have to check that whether that is okay when you are designed like this. In this case, the NO2 and F2 both are actual reactants of your Oro reaction. So you can you can be sure this should be your rate law, right? Okay, then what I make or rate law consider right? Okay, then. Again, I'm saying you this is how we are expected to derive the rate law with the use of the mechanism. Right? First, what we should do is first we have to write this thing. Rate of the overall process is actually rate of the source. Then write the rate of then write the expression to the rate of the source. This is written as all the steps are elementary, as the slow step is also elementary. So its rate can be written like this. Its rate constant and with its reactants with their stoichiometric value. So rate becomes like this. And then you have to check whether the things appearing here are reactants of the overall reaction. Yes, those are reactants of the overall reaction. So we can confirm this is the rate of the overall process. Correct? Correlation. Now, I write another one. Right? We'll discuss another one. Right? Right? See the next one. Right? Variable. Dia tahu dia kemudian di nomor ni kan? Beliau jadi set kerja bola tahu kan? See the second one. Example 2. So you have the oral process like this. NO2 gas reacting with CO gas, giving you NO gas plus CO2 gas. This is the oral process. And they have given the mechanism. Step 1 and step 2. Right? Step 1 is like this. NO2 gas reacting with another NO2 gas with K1 is giving you NO3 gas plus NO gas. Right? Then you have the NO3 gas plus CO gas with K2 you are going to get NO2 gas and CO2 gas. And they are mentioning this one as the source and the other one is soft. I just mentioned the source that is what we need. Right? Then let's try to come up with the rate law with the use of this mechanism. You can write the rate is equal to rate of source. Right? As the source state is also elementary, you can write the rate constant of source state into the reactant of source is NO2. You have two NO2. The only NO2 appears as a reactant at the source state. And you have 2 there. Stoichiometric value of NO2 is 2, right? This is just 2 of NO2. This is just 2 of NO2 giving you this. Right? This is just, you can write this as 2 of NO2 giving you this now. So 2, the stoichiometric value is 2 for NO2. So that can be applied as the order. So the rate law is this. then you have to check whether the concentration terms appearing here belongs to reactants of the overall expression, overall reaction. You have to check that. Yes, NO2 is the only species appearing at the concentration side as a concentration term. So NO2 is actually a reactant of the overall reaction. So it is okay. So this is your rate law for the overall reaction. Correct. Correct. Now, ලේසියෙන් අපිට rate law එක derive කරගන්න පුළුවන්. හරි? mechanism එක දන්නවනම්. හරි? අපි තව පොඩ්ඩක් මේක ගැන කතා කරමු. තව පොඩ්ඩක් මේක ගැන කතා කරමු. We have few things to discuss here. Right? Again. Right? Focus. Right. We have few things to discuss here. Few important observations to get from these two examples. Right? First thing, it is this. See, when it comes to multi-step reactions, the order with respect to reactants, may or may not equal to the stoichiometric values of the multi-step reaction. Order respective to X2 is 1. That is actually the same as the stoichiometric value. But order respective to NO2 is 1, which is not the stoichiometric value of the overall reaction. So, order respective to reactants may or may not equal to stoichiometric values of the reactants of multi-step reaction. In here as well, you see, the stoichiometric value here for the NO2 is 1, but here is 2. Here the stoichiometric value of CO is 1, here 0. Here 0. For anyone, the 0 power is just 1. Here CO is 0. That is 1. That is why the CO is not appearing. Right? So, order respective to reactant in a multi-step reaction may or may not equal to the stoichiometric values. It could be 0 even. It could be 0 even. It could be 0 even. It could be a value greater than the stoichiometric value. It could be a value greater than the stoichiometric value. Here is only 1, is 2. It could be a value less than the stoichiometric value. It could be a value less than the stoichiometric value. It could be a value which is similar to the stoichiometric value. All the things are possible with multi-step reaction. The order with respect to reactant could be same as stoichiometric value. It could be greater than the stoichiometric value, as well as it could be lesser than the stoichiometric value when it comes to multi-step reaction. That is one major idea to grab from these examples. All the things are there in the note. You can just read the stuff, and you can do highlight those stuff, right? Those are there in the examples, right? I just discussed, right? Okay, that is one thing. Next one, another thing, very important stuff, right? Very important stuff. This one. By looking at the rate law, you can say, you can comment on participation of some of the reactants of your overall reaction. What was it? ළමයි ඔයාලට rate law එක දිහා බලාගෙන overall reaction එකේ reactants ලා reaction එකට participate ලා තියෙන්නේ කොහොමද කියලා කතා කරන්න පුළුවන්. මේ බලන්න, you can say like this. It is all about this. this thing, rate law. Always remember this. In your rate law, this is the idea. This is the clear idea. In your rate law, only the species which will participate in your mechanism at your first step or prior to that will be indicated. Again, I am telling you, in your rate law, right? Only the reactant molecules, number of reactant molecules which participate in your reaction at this lowest step or prior to that will be mentioned. ළමයි rate law එකේ mention වෙලා තියෙන්නේ කවුද? mention වෙලා තියෙන්නේ oral reaction එක reactants ලා හැමෝම නෙමෙයි. ඔයාගේ mechanism එකේ slow step එකේදී හරි ඊට කලින් හරි වැඩේට involve වෙන කට්ටිය විතරයි මෙතන mention වෙන්නේ. අර 100 ගේ කතාව ගැන පොඩ්ඩක් හිතලා බලන්න. අර 100 ගේ කතාව ඔයාගේ කවුද? මකවාස්ගේ කතාව මතකයි? හරි? මේ කතාව පොඩ්ඩක් හිතලා බලන්න. 100 ගඩොල් කැඩ ටික පාස් කරනවා 800 bricks per hour. 800 bricks per hour. ඊට පස්සේ කට්ටිය 1000 පාස් කරන කැපැසිටි එකක් තියෙනවා, 1200 පාස් කරන කැපැසිටි එකක් තියෙනවා. හැබැයි ඒගොල්ල මැටර් වෙනවද රේට් එකට? නෑ, overall process rate is determined by the source step and prior to that ඊට පස්සේ ඒව වැඩක්ම නෑනේ. ඊට පස්සේ කට්ටිය capability එක වැඩක් නෑනේ. 100ට පස්සේ ඉන්න කට්ටිය grandfather පස්සේ ඉන්න කට්ටියගේ capability එක 1200 වුණා, capacity එක 1500 වුණාට වැඩක් නෑනේ ඒක reaction එක. slow step එක හරි ඊට කලින් කට්ටියගේ තියෙන reaction එක වැදගත් වෙන්නේ. The major stuff is the slow step. ඊට කලින් එකේ slow වුණොත් වැඩි ඉවරයි නේද? කලින් ඉන්න වැදගත්. හරි. එතකොට වැඩේට අතර වැදගත් වෙන්නේ ready-to-mind step එකයි ඊට කලින් ඉන්න කට්ටිය විතරයි. ready-to-mind step එකෙන් පස්සේ නම් if your reactant molecules are involving in your reaction after ready-to-mind step, then those are not written in your rate law. That is the whole idea. See, at this lower step or prior to that, only one NO2 molecule and one F2 molecule is involved in the reaction. That is why the NO2 soda is 1 and F2 soda is 1. At this lower step or prior to that, only one NO2 molecule and one F2 molecule is involved in the reaction. That is why the values are 1, 1, 1. So by just looking at this thing, you can say only one NO2 molecule and one F2 molecule is involved in the reaction at the ready-to-mind step or prior to that, so that you can say the other NO2 molecule, you have two here. The other NO2 molecule is involved in the reaction after the slow step. You can comment on that. You can say that. You can confirm that. By merely looking at this thing and this thing, even without looking at, even you don't know the mechanism, by just looking at this and this, you can say, okay, you have two NO2 molecules and one F2 molecule as reactants, but only one NO2 and one F2 participate at the reaction at this source step prior to that. The other NO2 molecule participated at the reaction after the slow step. That comment you can give. That is what actually truly happening. By just looking at these two stuff, even without the knowledge of the mechanism, even without the knowledge of this mechanism, by just looking at these two stuff, what you can say? You can say, even these are appearing like this. You can say two NO2 molecules are participating in your reaction at the slower step or prior to that, and CO molecule participate at the reaction after the rate determined step, you can see that. You clearly see, even without the knowledge of these things, by just looking at these two, you can say that CO is not appearing here. That means it is participating in the reaction after the slow step. Yes, that is the case. So those are the things you can grab from the rate law of a multi-step reaction. The CO is not appearing here because CO is participating in the reaction after the slow step. Remember, only the number of reactant molecules participating in your reaction at this lower step or prior to that will be indicated at the rate law. Only those. The others won't. Right? Got the idea? That is the total idea. See? Okay, those things are there. Right? You can highlight the stuff. Right? So at the page number 27, the bottom line, at the page number 27, the bottom line, right? You can highlight that. The second NO2 is involved after the RDS. The second NO2 is involved after the RDS. Just highlight that thing which is in bold letters. It does not appear in the oral rate law. As the second NO2 is participating in the reaction after the slow step, that is why it is not indicated here. At this case also, at the page number 29, at the page number 29, go to that. The bold color letters, bold letters. See, after this thing, it says involvement of CO gas in the mechanism is after the RDS. CO does not appear in the oral rate law. Just highlight the two phrases. Involvement of CO in the mechanism is after the RDS. So CO does not appear in the oral rate law. CO does not appear in the oral rate law. Right now? Just highlight the stuff. Rate law එකේ CO නැහැ කියලා කියන තේරුම මොකක්ද? CO මේකට ඉන්වෝල්ව් වෙලා තියෙන්නේ රේට් ඩිවර්ස් ස්ටෙප් එකට පස්සේ කියන්නේ. ඔව් මේක දිහා බලුවොත් අපිට පේනවා. මේ රේට් ඩිවර්ස් ස්ටෙප් ඊට පස්සේ CO වල දෙන්නේ ඊට පස්සේ. Right? Only the, you see, only the reactants of your oral reaction which participate in your reaction at this lower step or prior to that, only those will be indicated at the rate law. Remember that, that is the point. Right? ඊටික highlight කරගන්න. shape නේ. අපි තව එකක් බලමු. තව example එකක්. Just go to this example, which is at the page number 30. Which is at the page number 30. Let's go to another example, which is at the page number 30. Example, sorry, you know, अभी ये पूरा बाल. Page number 30 example. Example, page 30 will be. But the example is this one. This is the oral reaction. A plus B giving you P. The mechanism is given. A in a double arrow reaction giving you I. It's the fast step, the first step. Then you have the intermediate I reacting with B to produce P, the product. This is fast, this is slow. This is another example. And we have another situation at the page number 31. Example at page 31. We discuss both the stuff. You have this reaction, the oral reaction. The two steps are given. Two steps are given, right? Like I2 gas, 2O5 gas, and H2 gas, 2I gas. They are saying this is fast, this is slow. Okay. Let's try to come up with the rate law for these two mechanisms, for these two multi-separations. Deriving the rate law, right? Rate law rate law. Yes, you can write the rate law as rate is equal to rate of slow step. And it's okay. Always rate is equal to rate of slow step. What is the rate of slow step? If you take this one and the rate comes as k dash rate constant. You can write it as k dash into I into b, because all the elementary, all the slow steps are elementary, right? All the steps are elementary now. So you can put the stoichiometric values as order. Now the rate is given like this for the overall reaction. Then check. Then we have check. Then we have check whether all the things appearing here, whether those are reactants of the overall reaction. You check that, because for the overall reaction rate, only the reactants of the overall reaction should appear. For the rate of the overall reaction, rate law of the overall reaction, the reactants of the overall reaction should appear, not any other. So B is kind of a reactant at the overall reaction, but not the ideal. But not the ideal. Some intermediate is appearing here. That is not good. Some intermediate is appearing here. That can't be. Intermediates can't appear in a rate law. We have a problem here. Intermediates can't appear in a rate law. We have a problem. So you have to get rid of this intermediate. You have to get rid of this intermediate, because intermediates can't appear at the rate law of the overall reaction. Even though the slow step gives you like this can't be the finalized answer. So you have to get rid of intermediate. For that, we can use the equilibrium concept. We can use the equilibrium concept, right? As this guy is kind of an equilibrium, as this guy is coming up with the equilibrium, you can put this as Kc, the equilibrium constant. You can put that as Kc, the equilibrium constant, in terms of concentrations. So you can write the Kc. You can write the Kc as this, the I over the A. Equilibrium constants are written like this. Equilibrium constants are written like, you have to write the reactants, sorry, products, the concentration of products to its stoichiometric power divided by the concentration of the reactants to its stoichiometric power. That is how the Kc is written, right? So if you are to subject the I, it will give you the Kc into A. Why I have subjected the I? Because you can't have I here. So you have to get rid of I from this expression. So that I have subjected the I here, and I am going to apply that this term instead of I here. So you can write, instead of I, you can write the Kc into A. Kc into A instead of I, and the B is still appearing. So this is another constant. This is a constant. K dash is a constant. Kc is also a constant. So multiplication of a constant gives you a constant. So you can write this as K, A and B. This is your rate law. Now you clearly see there is no such term which is not appearing at the overall reaction. All the terms, concerned terms appearing here at the rate law now are reactants of the overall reaction. So this is acceptable. So this is acceptable as the rate law for the overall reaction. Right? So that is how we are going to get rid of intermediates if they are to appear at the rate of the source step. If the rate of the source step involves or comes up with some intermediate terms, we have to get rid of those things for the overall reactions rate law. We can get rid of those things with use of KC. Right? Let's do the same thing for this one as well. See? That is okay with that one as well. See? Rate can be written as the rate of source step. If you write the rate of source step, this is a source step, right? This is a source step. As it is also an elemental step, all source steps are element, right? So you can write take the k dash as its rate constant. So k dash into H2 gas into 1. The stoichiometric values can be applied as the orders, as it is a kind of elementary step. I gas into 2. That is the rate expression according to the source state. But again, we see the problem arising. This I gas is kind of intermediate, which is not appearing at the reactant side of the overall equation. I gas is kind of a intermediate. So we have to get rid of that I gas. So what to do? So you can apply the concept of equilibrium. You can apply the concept of equilibrium. So one can write the Kc for this equilibrium, the Kc for this equilibrium as the I gas squared. The stoichiometric value can be applied in the equilibrium constants divided by I2 gas products over reactants to the power of their stoichiometric values. So I gas, if you substitute the I gas, it is equal to Kc into I2. That is I gas squared. That is I gas squared. So you can subject this I gas squared here. So that will give you the rate as K dash into H2 gas. Instead of I gas squared, we can write this Kc into I2 gas. As these two are constants, okay, you can write that this is K dash into Kc. So H2 gas and I2 gas. As these two are constants, you can write it as K into H2 gas into I2 gas. This is your rate expression. Right? Okay, no? Right? So you clearly see, right? This rate expression is without any intermediates. You are without any intermediates. All the terms appearing at the rate law is there at the reactant side of the overall equation. So that is acceptable. Right? You home lamai ඔයා rate law එක derive කරන්නේ when the mechanism is given. Right? Again, see what I have told earlier. See what I have told earlier. When you are to examine this rate expression, you clearly see only one molecule of A and one molecule of B is participating in your reaction at the source step or prior to that. See, this is the source step. At the source step or prior to that, these are the reactant molecules involved. These are the reactant molecules involved. Right? See, one A molecule and one B molecule. That is why at the rate expression, you see one A molecule and one B molecule appearing. Right? One A molecule and one B molecule. Here as well. Right? This is the source state. This is the source state. This is the source state. So the rate law says that only one H2 molecule and one I2 molecule should appear at the source step or prior to that. You clearly see only one H2 molecule and one I2 molecule appears at the source step or prior to that. Source step එක හරියට කලින් ඉන්න කට්ටිය විතරයි බලන්න. මේකෙත් බලන්න. Source step එක කලින් ඉන්න කට්ටිය විතරයි. යට ඉන්න කට්ටිය වැඩන්නේ. Source step එක කොයිට කලින් ඉන්න කට්ටිය විතරයි. Right? So then you clearly see only the reactants in your oral reaction which participate in your process at the slow step or prior to that will appear at the rate law. Others won't. Others won't. Shape it. That is very important to answer to the MCQs. Right? That is the basic idea there. Right now? That is all about how we are supposed to use the reaction mechanism to come up with the rate law of the oral reaction. Right? Here again the intermediates should be cancelled off. So intermediates can get rid of intermediates with use of Kc values. Right? That is the idea. Okay, no? Right, that is how we are to use the mechanisms to come up with the rate law. Rate law. Yeah. So that is all about the page 31. You can clearly see the ideas appearing there. So I have discussed about the things appearing at the first 4 examples, no? Page 27, 29, 30, and 31. I have discussed about those mechanisms, right? And you can go to the mechanism appearing at the page 32 as well. Just go to the thing at the page 32 and see how they came up with the mechanism. I mean how they have came up with the rate law, right? That is what you need to do, right? So just complete that, and then we'll discuss how to write the energy profile next time around. Right? අපි next week එකේ කතා කරමු කොහොමද energy profile එක හරියට build up කරගන්න මොනවාද ඒකට සැලකුම් කාරණා කියන කාරණා අපි next day කතා කරමු. Okay, yeah, we have to go to for another lesson to complete this stuff, right? අපි තව lesson එකක් යන්න වෙනවා. අපි ඒකේ කතා කරමු කොහොමද energy profile එක complete කරගන්නේ කියලා, right? So if you have any questions, doubts, you can ask now. Questions not තියෙනවා පාට අහන්න පුළුවන්. No. Shape ne? හරි එහෙනම් අපි අද නවතිමු. right? ආයෙත් වීඩියෝ එකක් ගන්න උඩ බලන්න. බලලා මේ අයිඩියා එක ගන්න මේ බක් දෙකක් කාරණා කීපයක් කතා කරනවා. මේ දෙකකින් අපි ඉඳලා 3 week අපි කතා කරමු ටිකක්. හරි එහෙනම් අපි අද නවතිමු. and goodbye then. See you next week.